My name is Sean Kramer of the University of New Hampshire, and my research is in managing memory in C and C++, where we examine the vulnerabilities which plague these languages and analyze the existing security features in place. Before we begin, it is important to understand the difference between a vulnerability, an exploit, and an attack. Vulnerabilities are traits unique to a programming language or architecture which create the existence of exploits. In this research, the lack of boundary checking and manual memory management are vulnerabilities unique to the C and C++ languages. Exploits are specific methods of disrupting a program by taking advantage of these vulnerabilities. Some examples could be an out-of-bounds write, use after freeze, or double freeze. Lastly, attacks are the practices used to enact exploits. Common attack types are code reuse, return-oriented programming, and jump-oriented programming. Here is the hierarchy of software attacks. Beginning at the bottom, the attack types and the exploits they cause are closely intertwined with each other. At the next level shows two taxonomies which these exploits fall under, either control flow hijacking or memory corruption. At the top level, memory vulnerabilities stand as the reason to why these exploits and attacks exist. Though memory corruption stands as its own subsection, every type of exploit begins with triggering a memory error. Specifically for C and C++, boundary checking and memory management are placed entirely in the hands of the developer. As a result, the source code could contain numerous amounts of bugs, and finding and fixing all these programming bugs is unfeasible. Memory corruption deals with two types of errors. Spatial errors deal with space, where temporal errors deal with time. A spatial error can occur when an out-of-bounds pointer is dereferenced, while dereferencing a dangling pointer causes temporal errors. The primary goal of attackers is to disrupt the control flow of a program, but memory corruption is used to aid in this process. Notable attack strategies are return-oriented programming or jump-oriented programming. In return-oriented programming, the adversary manipulates the program's call stack to overwrite the return address with machine instructions which already exist within the source code known as gadgets. Jump-oriented programming relies on a similar attack pattern, the difference being that instead of overwriting the return address, the series of indirect jumps are used to chain together multiple gadgets. Existing security features for memory corruption involve the lengthening of code pointers or through a process called binary hardening. Each have their drawbacks. The concept of fat pointers is to encode code pointers with their base and bound, and each time this pointer is accessed, the current memory address is checked to see if it remains within these boundaries. Although this is effective against spatial errors, fat pointers have little to no impact on stopping temporal errors. Another drawback is the large overhead increase caused through software-only implementations. Binary hardening occurs at the compiler during runtime, where the binary is analyzed and modified to protect against potential access points. The benefit of this technique is that it does not require any modifications to the source code and can be used with legacy software. But similar to the fat pointer scheme, binary hardening accrues an overhead of at least 100%. A number of different security features exist for maintaining control flow integrity, but this presentation will only cover two methods which are currently deployed. Address space layout randomization, or ASLR, as implied in its name, randomizes the memory addresses of the library and source code. This increases the difficulty of attackers to predict memory locations of return addresses. There is no overhead involved, as it can be implemented through hardware, but researchers have proven that side channel attacks and information leaks can be used as a workaround that the security provides. Another method is stack canaries, which is a hardware implemented security feature which places a randomly chosen value right before the return address and will check it before executing the return instruction. The main drawback is that this relies entirely on one singular value, and once that is compromised, the entire security is compromised.